Hello and welcome to the stream. This is day 12. Yeah, day 12 of learning OpenGL. And today we're starting a new section, model loading with Assimp. Now this is the second time I'm recording this because the last time I tried live, I was actually unsuccessful in trying to get this to work. That was mainly due to part that this is not as exhaustive, like as in detail as it needs to be. Like here in the models chapter, there was some additional changes in the source code and they don't actually exactly tell you how to do that. But anyway, I spent a couple of hours trying to figure all this out, and we're actually gonna try this again. So yeah, let's just get started. Just before that, this is where we are right now. I actually just copied this project so we can delete all of this stuff and start from like a blank slate. I only want to put in the model loading stuff and not have all of this old stuff. So I'm just going to go ahead and delete this part where we have everything related to the all these boxes, the textures that we load, and all that stuff. So we don't need these old textures. We're actually going to use different textures. We're not going to need all of these vertices, view positions, or any of these lighting positions. So I'm gonna delete all of that. So we're gonna start from a clean blank slate. I'm even gonna clean out my render loop, and I'm gonna delete all of this drawing function, setting up our MVP matrices, and I'm gonna delete all of that. Yep, I think we're good. Let me just run this and we should have a blank canvas. Yeah, cool. Let's continue. So Assimp is a model loading library which we can download from here. Assimp is able to import dozens of different model file formats, which makes our job easier. And here we have a simplified representation of how Assimp structures its data that it loads in from the model file. It's showing that all the data of the scene or model is contained in the scene object. So this is like the main scene object, like all the materials and all the meshes. It's showing like it has an array of meshes and an array of materials. It also contains a reference to the root node of the scene. So this references this root node, which itself has an array of children, which can have their own array of children, and it just goes on recursively like a tree. And then it also has array of meshes, and here it's showing that this contains the index to a mesh in the scene.meshes. So this meshes actually references, it only contains an index and it references this meshes array which is inside the scene. So the root node of the scene may contain children nodes like all other nodes, and could have a set of indices that point to the values in the meshes array of a node are only indices for the scene's mesh array. So all the data is within this, but which data corresponds to which node is that information is held within each of these nodes. And then what do these meshes contain? They contain the information related to it, like the vertices, the normals, texture coordinates, and what material indices they have. And these material indices are actually just references to this material array. So this is actually a very intuitive way of having all of this data. A mesh object itself contains all the relevant data required for rendering. Think of vertex positions, vertex normals, and all that good stuff. A mesh contains several faces. A face represents a render primitive of the object, triangles, squares, points, etc. A face contains the indices of the vertices that form a primitive because the vertices and indices are separated. This makes it easy for us to render via an index buffer. Finally, a mesh also links to a material object that hosts several functions to retrieve the material properties of an object. Like if you want to know what the color is or what texture maps are used for it, like if you want to know the diffuse map or the specular map, all of that information will be within the material object, or maybe it's a struct. What we want to do is, first we want to load an object into a scene. into a scene object, and then recursively retrieve the corresponding mesh objects from each of the nodes. We recursively search each node's children. The process each mesh object to retrieve the vertex data, indices, and its material properties. The result is then a collection of mesh data that we want to contain in a single model object. Okay, so this is the data structure of what Assimp creates, but then we want to retrieve all of this data in a way that we can send it over to the GPU for input. So this part is for building Assimp, and that's what we're gonna do. I've actually done this before just to see that it works. But the steps are, I just went to the installation link and clicked on the build instructions. This takes you to the GitHub link, and I actually followed the first one, but this gave me like a 32-bit version, the x86 build, and I tried using that, but my project is 64-bit, so it actually did not work. So that was a waste of time. And then I followed these instructions. I made it from CMake, and this part actually did work. I just cloned this, cloned the repo, cd'd into the directory, which is right here in my downloads folder. So it cloned this, I cd'd into it, and then I ran cmake list.txt, and then cmake --build. And that generated the files. So it gave me the bin file, the DLL. That's what we're gonna need, and it also gave me the lib file. Should be right here inside the lib. This is the lib file. We're gonna need that as well. And finally, we have the include files. These are the three things that we need to put in our project. So I'm just gonna copy the include file, and I'm gonna open my project in another tab. Yeah, and I'm going to copy the include files and put it in include folder and put it inside right next to the other include folders. And I'm going to copy the lib file, this one, assimp vc143-mtd, and I'm just going to copy it and put it inside the lib file, lib folder right alongside my glw.lib. And finally, we need the DLL, and the DLL is just going to be right here in a root directory where our project is. I'm just going to go into bin and get this this DLL. Just copy and paste it into our project directory. So now we need to tell Visual Studio that we are going to link against this library. So I'm just going to copy the name of this and open up Visual Studio, go to project properties, and under linker input, right here we have our glw.lib, and right before that I'm going to paste this and add a semicolon to separate it, and I'm just going to press OK. So if I compile this now, this should not give me any errors. That means the linker successfully linked with our lib file. So that should be good. We should be good now. Assimp has been added to our project. Let's move on to the next chapter for meshes. With Assimp, we can load many different models into the application, but once loaded, they're all sorted in Asimp's data structure. What we eventually want to do is transform that data to a format that OpenGL understands so that we can render the object. We learned from previous chapter that a mesh represents a single drawable entity, so let's start by defining a mesh class of our own. Okay, let's add a mesh class. I think it creates just a header only class, so that's what we're gonna do. Just gonna right click on header files, add new item, select header files, and I'm gonna call this mesh. So the first thing we're gonna do is create a struct for our vertices. It's gonna have the information like position, normal, and texture coordinates. It seems like we need to include GLM, so that's what I'm gonna do. copy GLM, and let's put it here. And the next thing we need is the texture struct. It has an ID and string type, so that means we're gonna need to include string. And it's not using std. Let's also just get our namespace. All right. So we store the ID of the texture and its type as, for example, a diffuse and a specular texture. Knowing the actual representation of a vertex in the texture, we can start defining the structure of the mesh class. So this is the structure of our mesh class. We're going to have a vector or a list, you could say a list of vertices. We're going to have a vector of indices and a vector of textures. So let's just include vector. We're going to have a constructor where we pass it the vertices, the indices, and the textures. And we're going to have a draw function. And for that, we need to pass it the shader. So let's include the shader class. All right, and we obviously gonna have our VAO, the vertex buffer, and the EBO. And finally, we have the setup mesh function, which I assume is a helper function. As you can see, the class is too complicated. In the constructor, we give the mesh all the necessary data. We initialize the buffers in the setup mesh function, and we finally draw the mesh via the draw function. Okay, so for our constructor, all we're gonna do is take these parameters and store them inside our class's member variables, and finally call the setup mesh function. That seems simple enough. Let's just copy and put it instead of the prototype. And for the initialization, this is our setup mesh function. What we're doing here is the code is not much different from what you'd expect, but a few little tricks were used with the help of the vertex struct. Struct have a great property in C++ that their memory layout is sequential. That is, if we were to represent a struct as an array of data, it would only contain a struct variable in sequential order, which directly translates to a float, actually byte, array that we want for an array buffer. For example, if we have a filled vertex struct, its memory layout would be equal to vertex of type vertex, and then vertex dot position is this, vertex dot normal is this, and the vertex code is this. So it's just saying similar to how we were defining the arrays in our main function, and that we were laying out all the data sequentially. So the first three floats are going to be our position, these three floats are going to be our normal, and the last two floats are going to be our texture coordinates. It's the same as having them in a struct, because struct is also laid out sequentially. So that is what we're doing in our setup mesh function. This is the same thing that we're doing for OpenGL, GL generates arrays, generating our VBO and EBO, and then binding the data to it, enabling our vertex attrib. And here we're taking our vertex struct. This here is just the starting of the struct, but to define the normal, which would start from over here, what it's doing is it's using the offset off function, passing it the struct, and then saying the name of the property. Here, over here inside the struct, we have position, normal, and texture coordinate. So the normal is the name of the property inside the struct, and when we pass to the offset function the name of the struct and the name of the property, it will actually give us the offset, how many bytes it is from the starting of that vertex. And then obviously it's going to cast it to the void pointer like we've been doing. And then finally Okay, yeah, we can just copy this whole thing and replace this. Set up mesh over here. That leaves our draw function. The last function we need to define for the mesh is the draw function. Before rendering a mesh, we first want to bind the appropriate texture before calling GL draw elements. However, this is somewhat difficult since we don't know from the start how many, if any, textures the mesh has and what type they may have. So how do we set the texture units and the samplers in the shaders? To solve the issue, we're going to assume a certain naming convention. Each diffuse texture is named texture diffuse N, and each specular texture should be named texture specular N, where N is the number ranging from 1 to the maximum number of texture samples allowed. Let's say we have 3 diffuse textures and 2 specular textures for a particular mesh. Their texture samplers should look like this. Okay, so this is like a naming convention that we have set up. By this convention, we can define as many texture samplers as we want in the shaders up to OpenGL's maximum. And if a mesh actually does contain so many textures, we know what their names are going to be by this convention. You can process any amount of textures on a single mesh, and shade developers is free to use as many of those as he wants by defining the proper samplers. Okay, so this is our draw function. We are passing it the shader. Here we're setting up the number of diffuse textures and the number of speckle textures. We are going to loop over, we're going to make a loop and then textures.size. Okay. Here we have GL active texture, GL texture 0 plus 1. So that's how we're going to activate the appropriate texture unit before binding it. Retrieve the texture number, the N in diffuse texture N. So string number, name, textures at I. So wherever we are in the loop, dot type. That'll give us whether it's a diffuse texture or a speckled texture. And if name is texture diffuse, then it's gonna do diffuse and number, and then after it passes it to string, and then we're just gonna increment diffuse and R++. And if it's specular, we're gonna do the same thing but with specular. And finally, it's doing shader set int material dot and the name of the texture and finding the number of the texture. So that's like following our convention of naming. And then finally, it's gonna bind that texture. And then finally, we're going to draw the mesh using GL draw elements, GL triangles, and it's going to be equal to however many indices we have. Okay, let's just copy this function and put it instead of our draw function prototype. So that is our mesh class. Here it's defining what we're doing. We first calculate the n component per texture type and concatenate it to the texture's type string to get the appropriate uniform name. We then locate the appropriate sampler, give it the location value to correspond with the currently active texture unit, and bind the texture. This is also the reason we need the shader in the draw function. So we need the appropriate uniform name because we're going to define all of these inside our shader. Let me just grab the shader that we're going to use. Here in Learn OpenGL from the GitHub, we can get our shader. So this is our fragment shader and this is our vertex shader. Here you can see that we're only using texture diffuse 1, so it's only using a single texture, a diffuse texture, and it is following the same naming convention, texture underscore diffuse, and then the number, which in this case is going to be 1. So let me just download both of these. And I'm going to call it model loading.fs, and for the vertex shader I'm going to call it model loading.vs. Okay, let me just copy both of these into my project. Might as well create a new folder, call it shaders. Okay. Since we're starting from a blank slate, I'm gonna delete all of my old shaders and any of these textures that we're not using right now. It's okay, I have a backup of this project, so I'm not completely throwing it away. Okay, we have our shaders. Our mesh class is also done. Let's move on to the model class. Now it's time to get our hands dirty with Assimp and start creating the actual loading and translation code. The goal of this chapter is to create another class that represents a model in its entirety. That is a model that contains multiple meshes, possibly with multiple textures. A house that contains a wooden balcony tower, blah blah blah. So just give an example of a model, and the model can have multiple meshes. So this is our model class, and here we have all the signatures of all the functions that we're going to have. Here we have a public constructor. This takes a path. Okay, it takes a path to the model that we're going to load, and then it calls the load model function. And then we also have process node, process mesh functions. I'll just copy this and create our model class. Add a new item, add a file, and I'm going to call it model.h. So we're going to need to include some stuff. First of all, we need the string, the vector, and the shader. Just copy this. We probably don't need GLM, so I'm not gonna do that. Okay, and all this I think comes from Assimp, so we're gonna probably need to include that as well. The model class contains a vector of mesh objects that and requires us to give it a file location in its constructor. It then loads the file right away via the load model function that is called in the constructor. The private functions are all designed to process a part of Assimp's import routine, and we'll cover them shortly. We also store the directory of the file path that we'll later need when loading textures. The draw function is nothing special and basically loops over each of the meshes to call their respective draw function. Okay, so this is our draw function. It just takes in the shader, loops over all of the however many meshes we have in the model. So we get that by meshes.size, and then meshes at i.draw. Okay, so we're going through all the meshes and we're drawing them using our draw function. So this is our draw function. I'm just gonna copy that a sec. Okay, yeah. Then we have importing a 3D model into OpenGL. To import a model and translate it to our own structure, we first need to include the appropriate headers of Assimp. So we're going to need Assimp importer, Assimp scene, and Assimp post process. Let's copy that. That should get rid of all of these errors. Okay, we're also going to need our mesh, this mesh.h. Let's include that. And yeah, that gets rid of all of errors. The great thing about Assimp is that it neatly abstracts all the technical details of loading all the different file formats and does all this with a single one-liner. We're going to create an importer of type Assimp importer, and then we're going to have a const AI scene, and we're going to call the importers function read file. We pass it the path, and then we tell it to do some post-processing, AI process triangulate, and we can or that flag with AI process flip UVs. First, we declare an importer object from Assimp's namespace and call its read file function. The function expects a file path and several post-processing options as its second argument. Assimp allows us to specify several options that forces Assimp to do extra calculations or operations on the important data. By setting a process triangulate, we tell Assimp that if the model does not entirely consist of triangles, it should transform all the model's primitive shapes to the triangles first. and flip UV flips the texture coordinates on the y-axis where necessary during processing. You may remember that the textures chapter that most images in OpenGL were reversed around the y-axis. This little post-processing option fixes that for us. A few other useful options are gen normals, split large meshes, optimize meshes. I don't think I'm going to use those. Assimp provides a great set of post-processing options that you can find all of them here. Loading a model via Assimp is, as you can see, surprisingly easy. Okay, so this is our load model function. Let's copy that and put that here. After we load the model, we check if the scene and the root node of the scene are not null and check one of its flags to see if the return data is incomplete. If any of these error conditions are met, we report the error, retrieve from the importer's getError string function, and return. We also retrieve the directory path of the given file path. Okay, so all we're doing is doing the import here using Assimp importer and checking if the import was successful or not. And then we're getting the directory from path dot find last of slash. Okay. And then finally process node scene arrow mroot node, and then we're passing it scene. All right, if nothing went wrong, we want to process all the scenes nodes. We pass the first node, the root node, recursively to the recursive process node function because each node possibly contains a set of children. We want to first process the node in question and then continue processing all the nodes, children, and so on. Okay, so this process node is going to go through each node and then recursively go through their children and their children and so forth. So let's copy the process node function. Paste that over here. So as you can see, we're looping over however many meshes we have that's stored inside mnum meshes, and then we're retrieving the mesh. Meshes dot pushback process mesh. Okay, we're adding it to the meshes vector. After we call the process mesh on it, we haven't defined that yet. Then do the same for all of its children. So, and then it's going to do node arrow mnum children. So however many children it has, it's going to call process node on that. Okay, we first check each of the nodes mesh indices and create the corresponding mesh by indexing scenes m meshes array. The returned mesh is then passed to the process mesh function that returns a mesh object that we can store in the meshes list or vector. Okay, so after that is done, we need the process mesh function, which we call right here. We're gonna pass it the Assimp mesh object and the AI seed. What is it doing? We have the vertices indices in the texture vector. We are looping over our however many vertices we have, and then vertex. Okay, process the vertex position normal and texture coordinates. We need to do that, and then process the indices. Okay, and then finally we're returning the mesh. Cool. So we need this process mesh function, but this, as you can see, is not complete. They have added ellipses. What we're actually gonna do is, okay, they're adding it one by one. That's fine. We're just gonna copy the whole thing from this source code. This is the model class, and the function we want is process mesh. Okay, yeah, this is our process mesh function. It actually does a whole bunch of extra stuff that they don't show here, which is very counterintuitive, especially for learning material. But I did go through it, and as you can see, it does show a bunch of errors. The vertex does not have these tangent and bitangent properties, as you may have noticed here. We only have position, normal, and texture coordinates. You can go ahead and add those if you want, but I'm just gonna take the shortcut and delete these out of here. We don't need that. So that is our process mesh function. Cool. And that finally leaves us with the load material textures function, which we have right here. It takes the material, AI texture type, so whatever the type is, and finally the type name. We are creating a vector of textures and then going through however many textures that material has. So get texture count. Okay, we're also passing the type, so it needs to know what type of texture we want. Okay, and then finally it just adds that texture. It gets the texture from the file. So we have a texture from file function, and then it puts that texture inside our textures vector, and then it returns that vector. All right, let's copy that. Cool. So you may have noticed two errors here. You need to copy this correctly. Yeah, two errors here. Texture from file, that function does not exist, so we do need to create that. Okay, load material textures. Load material textures. Okay, this is actually a modified version of the same function. Might as well use that. Yeah. So first we need textures. Okay, first we need texture from file function, which as you can see is not defined here, even though it is called in this example. What you have to do is go to the source code and get this function, texture from file, copy that. I don't know if this is an oversight or they don't want to show this, but anyway. So what this needs is the STB image library, so let's include that. That gets rid of a few errors, but we also need this textures loaded property. It actually talks about it here. We're not completely done yet, since there is still a large but not completely necessary optimization that we want to make. Most of the scenes reuse several of their textures onto several meshes. To think of a house again, you have granite texture on its walls, and then you have the same texture on the floor or on the ceiling. So one texture can be used in multiple places. Rather than loading the same texture again and again, what we can do is we can have a vector called textures loaded, and whenever we see the path of the texture, we can check if this texture has already been loaded or not. And rather than loading it again, we can use the same texture that's already loaded. So for that, we're gonna need to add this path of the texture so that we can store the path. Okay, let's paste that here. And that gets rid of that error. Okay, what is this? So the texture from file expects some variable that we are not using here, so it's okay, we can get rid of that. Okay, so there are no more errors. Cool. So that is our models class. We should be able to load it, but we first actually need to get that model. So let's just save that and put it in our project once it's downloaded. Okay, yeah, I'm not going to download that. It's going to take some time. My internet is kind of bad. I already have the model downloaded, so I'm just going to take it from here, I believe. Yep. And paste it here. So basically I have created this resources folder. Inside that I have the models folder, backpack, and here you can see we have all the textures that we need and the obj file, which is the model itself. Okay, I'm not sure if I can open it. Yeah, this is the model. It looks weird on this. but hopefully it'll look better when we import it. Okay, so that's our model. And how do we do this? I'm not sure. It doesn't show it here. Again, you have to go to the source code, and this model loading.cpp, this shows you how to actually use the classes that we have created. If you just come right here, first of all, we need to create the shader that our model is going to use. So let's copy this. Right before our render loop, we're going to create our shader. Make sure you call your shaders the correct thing. I've named them model loading.ps and model loading.fs. So that's our shader. It's called, well, our shader, unsurprisingly. And finally, to load the model, we're going to create an object of the model class, and it does it this weird way. After experimenting with this a little bit, I found that you don't actually need this file system go get, but I don't know why it's doing it. Maybe it's, I read somewhere in the comments, it's got something to do with the Mac. On MacBooks this does not work, but that's fine. Okay, we're just passing it as string, and here our model class is complaining, and to fix that, in the constructor it's actually expecting with the constructor it's expecting a char pointer. Rather than doing that, I'm just gonna pass it a string const pointer. This is our load. Okay, yeah, we can do the same thing here. That's causing issues. Let's just keep it simple, pass it a string, and that should get rid of the error right here. Oh, okay, we also don't have the model included, which is weird. Let's do that. Include our model.h. Just to make sure this does actually throw an error. Yeah, so it does complain that this does not match the type because we're passing it a const char array, and so we change this to string, and that fixes the error. Okay, so we have our model loaded. Now we have to display it inside our render loop. So this is also the same thing that we've been doing previously. First we set our view and projection matrices, and then it's setting its model matrix, doing some translation and scaling using that model matrix, and then setting it in our shader, and then finally calling our model.draw function and passing it the shader that we have created. Okay, it has this screen width variable, but I'm calling them window width and window height. So I'm just gonna rename them, and we should be good. Let's give that a try. Okay, we seem to have some errors. Shader compilation has failed. Okay, yeah, I don't think I'm passing the correct path, even though this name is correct. It actually, I need to qualify it with the whole path, and it's under shaders. TERS, yeah. Shaders slash and then the name of the shader. Same for the vertex shader. Let's try this. Okay, there's still some error. Okay, I think I know what the error is. The path of this model is not correct. Okay, I have resources. I'm not calling it objects, I'm calling it models. Then backpack.obj. We should be good. There are no errors. Okay, I see something. There are no errors here. Okay, I can't move around or anything. Okay, let's take a look. Yeah, so these are our vertex shader and our fragment shaders. They look to be correct. I just downloaded them directly. Okay. Could be an issue with the shader. So it's not throwing any error or anything like that. I mean, it clearly loads the model. I can see the outline. As you can see, there's no error in the console, nothing here. Okay, let's get rid of these. Nope. Okay. Let me just reference my test project. I'm just gonna open this project. Okay. Nope, still not working. Maybe it's a problem with the model file. Nope. Okay, maybe I'm not loading it correctly in our main function. Because the model does correctly seem to be loading correctly. The problem seems to be either with the textures or with the shaders. Okay, I'm not doing the STBI set flip vertically on load, but I don't see why that would not show the textures at all, but still worth a shot. Nope, still not showing the texture. Could my model file be problematic? Just check that. Okay, let me just copy the model once again. And give that a try. Nope, still something is wrong. Okay, just checking my test project. Yep, this seems to be working fine. Okay, now this seems to be working. So there's clearly some mistake I'm making in the main LCP. Here, okay. Just try to see what am I doing. We got our shader, camera, and model, and our STB images here. Then we have our GL report, enable depth test, and then STBF vertically on load is set to true. Our shader is set to shaders. Model loading.vs, this seems all fine. Our model is also correct. Maybe something's wrong in the render loop. Ah, yeah, got it. So right before I'm setting our shader, I actually need to use our shader. So our shader.use. So we actually activate our shader before setting all of these matrices, and that should fix our problem. And our model is loading correctly with the textures. Yep, cool. Not sure if I can resize the window. Okay, yeah, that looks weird. Okay, yep. I think that concludes the stream. That was day 12 of learning OpenGL. We successfully loaded the model using the Assimp library, and that also finishes this chapter. And the next chapter is going to be advanced OpenGL. So this is just like a random assortment of like advanced techniques. So we'll be checking those out next week. Thank you for watching. The stream has been going on for 50 minutes. All right, I can just plug in my YouTube channel real quick. You can go to youtube.com/@codestrum. Yeah, I did mean youtube.com. And you can check out all of the previous days. Just check out this playlist of all the live streams that I'll be doing. I'll be adding this as well. If you are watching this on YouTube, you can actually catch me on Twitch, twitch.tv/codestrum. And this is where I live stream every weekend. Currently, I am doing this. Hey, that's me. All right, thanks for watching. See ya.